There are many situations in applied mathematics where we use approximations. We approximate complicated functions with simpler polynomials. A common example of this is when we compute Taylor series. We can use periodic functions to approximate more complicated functions, even those which aren't continuous, using Fourier series. And we can approximate models to make sense of data using machine learning. In all of these cases, the goal is to find the best approximation for a given problem. But what is a best approximation? We start with a set capital B, which is a metric space. Inside capital B, there is a point f we wish to approximate. But to approximate f, we are only allowed to use points in a set capital A, which is a subset of capital B. Because this is a metric space, we have a measure of the distance between any point in A and f. Therefore, we say the best approximation from capital A to f is the element in capital A with the smallest distance to f, and we call this A star. More formally, we say A star is the best approximation from capital A to f if the distance from A star to f is less than or equal to the distance between f and any other A in the set capital A. The previous definitions were a little abstract, so let me give an example. Let capital B be the set of continuous functions over a given interval. And let's choose an element of capital B. Let's say f is equal to e to the minus x. Let capital A be the set of polynomials of degree 2. And notice that this is a subset of continuous functions. We can then define the distance between any function A in capital A and f as a L2 norm of A minus f over the interval. In this case, the best approximation from capital A to f is the function A star, which minimizes the L2 norm of A minus f. We'll now show that this so-called best approximation exists regardless of which f we choose. Stated as a theorem, we say that if capital A is a compact subset of a metric space capital B, then for every f in capital B, there exists an element A star in capital A such that the distance between A star and f is less than or equal to the distance between f and any other element in capital A. Notice that we are dealing with a compact set of approximations. Let me first explain why before getting into the proof. The compactness of our approximation set capital A ensures that the best approximation can be reached. A compact subset of a metric space is closed and bounded. Consider approximating the number 2, and you're given two sets. The open interval from 0 to 1, which doesn't include the endpoints 0 and 1 and isn't compact, and the closed interval from 0 to 1, which does contain the endpoints and is compact. In the open case, we can create a sequence of numbers which get closer and closer to 1, which of course would be the best approximation to the number 2, but we never actually reach the best approximation because it isn't in the open interval. Therefore, for any approximation in the interval, you can always find a better one. In the case of the closed interval, we find that the same sequence converges to 1 and 1 is in fact in the set, since no other number in the closed interval from 0 to 1 is closer to 2 than 1, we've found the best approximation. So taking the distance function as a function of x in our open and closed intervals, if we plot the distance between x and 2, we can draw a line to our minimum distance d star, which has a value of 1 and occurs when x is equal to 1. In the open case, although the distance function approaches the minimum distance d star, it never actually reaches it. On the other hand, the distance function on the closed and compact set actually reaches the minimum distance d star. So we've established that there exists a minimum distance between f and the set of approximations capital A, and we call this distance d star. We now need to show that there is an element of this set which actually is this distance from F and is closer to F than any other element in capital A, or at least the same distance. This is where the compactness of capital A becomes very useful. We can say that there exists a sequence of elements A sub I in capital A such that the distance between A sub I and F converges to D star as I tends towards infinity. Let's call the limit point of this sequence A plus, and to give away the ending, we'll now show that A plus is the best approximation to F. To show that A plus is the best approximation, we need to show that no other element of capital A is any closer to F. Consider the area immediately around A plus. Since A sub I tends to A plus, and the distance between A sub I and F tends to D star, let epsilon be a small number greater than 0. If we construct an open ball around A plus with a radius of epsilon over 2, we can guarantee that there will be some number k such that A sub k lies within this ball. This implies that there exists an element A sub k which simultaneously has a distance less than epsilon over 2 away from A plus and a distance less than D star plus epsilon over 2 away from F. From the triangle inequality, we have the distance between A plus and F is less than or equal to the distance between A plus and A sub k, plus the distance between A sub k and F. Now we already have inequalities for both of these distances on the right hand side, and adding these together shows that the distance between A plus and F is bounded by D star plus epsilon. Since epsilon can be made as small as we choose, then the distance between A plus and F is D star, and so A plus is the best approximation. So there we are. We found that when making approximations in a metric space, it's possible to show that there's at least one point A star in capital A, our set of approximations, such that no other A in capital A is close to F. And A star is therefore the best approximation from capital A